the last lecture, we looked for the first time at short duration loads, and I introduced the concept of the shock spectrum, and also we solved some typical kind of solutions. In this lecture, we are going to be looking at the pulse load response characteristics, and also we will introduce the concept of impulse loading. Now, pulse load response characteristics. Actually, to illustrate this, I would like to take a specific kind of loading and let us go through the process of having gone doing this. And for this, I will actually solve a problem which does not look like a pulse load. Okay. This is T, this is P of T, continues like this. Now, does it continue like this? Well, actually it does not, but it does not matter now. Let us assume that it continues. Okay. And this I will call as T r. Okay. So, and this one will be P naught, and so therefore, P of T can be written as T r for 0 T T r, okay, and it is equal to P naught for T greater than T r. So, in other words, there are two solutions, and what I am going to do is I am going to now assume that T r by T, okay, is let us say less than 1, okay, actually substantially less than 1, okay, and therefore, the duration of the load does not really matter, because T r by T is substantially lower than 1. Okay. So, let us look at this solution. Now, since the load is of two types, actually I have now here again, this is different. This is not phase 1, phase 2 as we know it. This is just that the load phase 1 and load phase 2, and T r is the rise time of the load from 0 to maximum. Okay? T r is the rise time of load from 0 to maximum. Okay? That is why I have defined it as T r, whereas earlier I had duration of load. Okay? But there is a specific reason why I am presenting this, because this will give me some idea about what I am talking about characteristics. Okay? So, now let us look at how to solve, and now the thing is that since it is very small, okay, I am going to still continue to solve the undamped system, because understand that since T r is much less than 1 and even in phase 2 the peak will occur somewhere in the beginning. So, for all practical purposes damping does not come into the picture, and so I shall only continue to solve this problem, okay, because I am looking at pulse load characteristic, response characteristics, and that is why to highlight that I will continue with the same thing. Okay. So, load phase 1, load phase 1, what happens? Well, let us see. Okay. You are solving m u double dot plus k u is equal to P naught T upon T r. Okay. And so, if you look at it, particular solution is really P naught upon k into T r. And so, without going into too many details, okay, since this is of T r, what we will get is cosine term will have 0. So, only the sine term will exist, and so it becomes essentially u of t is equal to a sin omega t plus p naught. Understand that u dot equal to u dot equal to 0 at rest initial conditions. So, this is the solution, and this solution by plugging in u dot, which is equal to a omega cosine omega plus p naught k 1 upon T r. Okay. So, essentially what happens over here is that a becomes equal to, a omega is equal to p naught upon k. So, a omega is equal to p naught upon k into 1 upon T r, and so this becomes p naught upon omega k. Omega k is 2 pi upon t. So, this basically a becomes p naught by k, and what do you have? You have 2 pi over here. So, it is 2 pi, and on top I have t upon T r. So, this becomes my A, and so therefore, the solution of the first load phase solution essentially becomes what? It becomes u of t. So, this is load phase 1, u of t is equal to, and I can put p naught upon k outside. I will put p naught upon k outside, and inside I have t. I am sorry, this becomes the following. I have made a mistake. This plus this is equal to 0. So, this becomes minus. So, this becomes p naught k t upon T r minus 1 upon 2 pi t upon T r sin 2 pi t upon T r. Sorry, t upon t. This is t. Okay. So, this becomes the solution of the first equation. Okay. Load phase 1. So, now load phase 2, how does load phase 2 work? Load phase 2, essentially I have to have u t r and u dot t r, and then look at the rest of the thing. So, what is u t r? U t r is equal to t upon T r. So, this becomes p naught upon k. T r upon T r is 1 minus 1 upon 2 pi t upon T r sin 2 pi T r upon t. Okay. So, this is what I get for my u t r, and similarly u dot t r, if I double differentiate this, I get p naught k, and I am going to put T r outside. So, I get 1 minus, you see this one becomes cosine 2 pi upon t. So, this goes, so this 2 pi cancels, t and t cancel, 1 upon t r goes outside. So, this becomes 1 minus cosine of 2 pi t r upon t. Okay. So, the point to write down is that in load phase 2, I get u t r, okay. So, these are my u t and u t r's. So, my u t becomes a sine omega t. Again, omega t is nothing but 2 pi t upon t. So, I am not writing it down in cosine omega, and this one I am going to make it as t minus t r, be cosine t minus t r. The reason why I am taking t minus t r is because then t r will become 0, right. Okay, so, that is all I am doing really. So, a cosine t r and then plus what is the thing? It will be p naught. So, it will be p naught upon k u of t. Okay. So, this is the solution. I am writing it in this fashion purely to ensure that you get your this thing. And so, therefore, what do I get? I get, if I substitute in here, I get u t r is equal to b. Note that sin t minus t r at t r is going to be equal to 0. Okay, so, this is going to disappear. This is going to be b cosine omega t upon t r, that is 1 plus p naught by k. So, your b is equal to minus p naught by k, and what you have is, if you look at differentiation, this becomes sine, this disappears. So, this one becomes what? A is equal to u dot. So, A is equal to u dot t r, I am sorry, B becomes u t r minus p naught upon k, and this becomes u t r upon omega. Okay. And so, ultimately the phase 2 solution becomes the following. Please follow the mathematics, because the mathematics is important to what I am discussing, but later on, after the mathematics is over, the physical part is what we are going to be concentrating on. So, the mathematics is important only in so far as to get us to where we have this. Okay. So, let us look at this. So, this becomes then ultimately the u of t becomes equal to a. So, this is going to be u dot t r upon omega into sine 2 pi by t into t minus t r plus u t r minus p naught upon k cosine of 2 pi t minus t r and plus p naught upon k. So, this is load phase 2 u of t. Okay. So, now the question becomes that let us expand this, and I am not going to subject you to the stress of how to expand it, but if you write it down, then I get the following. I can take p naught upon k outside, and I have 1 plus t upon 2 pi t r cosine 2 pi t r by t minus 1 sine 2 pi t upon t minus sine 2 pi t r upon t into cosine of 2 pi t upon t, and this then gets. So, that is your u of t for load phase 2. So, therefore, for load phase 1, this is my u of t, and for load phase 2, this is my u of t. Okay. So, what does it give me? Well, let me try to look at it. When t by t r tends to 0, where will the peak occur? Note that if t by t r tends to 0, load phase 1 practically disappears. So, it essentially is that you are in load phase 2. So, the peak will occur in load phase 2, and if you look at load phase 2, what do you get? You get sine 2 pi t r upon t is equal to 2 pi t r upon t. Okay. Then cosine of 2 pi t r upon t tends to what? Is equal to 1, and essentially u t r and u dot t r tend to 0. Okay, because if you look at this, okay, sin 2 pi upon t r, this becomes 2 pi upon t r, 2 pi upon t r 1, 1 minus 1 0, and this becomes 1 minus 1 0. So, both of them are 0, okay, and this is what happens. Okay, if you have that, then these disappear, this becomes 1 minus 1, this disappears, this becomes 2 pi. So, this is cancelled with that, and so what I have is 1 minus. So, my u of t becomes p naught upon k into 1 minus cosine 2 pi t by t. Okay. And what is the maximum for this? To p k naught. Okay. Very interesting, and that is that let us see what does that mean. If I look back at this, all I am saying is that, well, this basically becomes like this, and that, as we know, is like the triangular pulse, where if the triangular pulse lasts long enough, u max is equal to 2. We know that long enough, this, as long as it lasts more than t d by t, it becomes 2 pi. We have derived this through this concept. Okay. Secondly, interestingly enough, if we try to get, if we take t r upon t to infinity, in other words, what does that mean? That the rise time is exceedingly slow. So, therefore, note something, that just by setting up the load time, just by setting up the rise time. So, I am saying that one rise time is really fast, and the other rise time is very slow. T r by t tends to infinity. Actually, it does not tend to infinity, it is just long enough. Okay. If it is long enough, then what happens? Well, let us see again. We know that this will be in phase 1. If this tends to 0, this implies that T by T r tends to 0. So, if T by T r tends to 0, then u of t in phase I mean it will be in phase 1 obviously, and phase 1 u of t is equal to P naught upon k T by T r. Well, let's solve it. Let's look at it. I mean, why go through it? Let's just look at load phase 1. Load phase 1 is this, and when T by T r tends to 0, this term drops out, and what you have is this term. Okay. So, it is P naught T upon T r, okay, and u dot t. Well, let's see what is u dot t. 1 minus cosine. So, this T r upon t, okay, when I put T r in here and I put t here, I get that this becomes essentially equal to 1 minus 1, because this term, okay, goes to 0. Okay. So, essentially u t goes to 0. So, what is the value at the end of the phase 1? Well, P naught upon k. So, maximum, if I look at maximum, maximum will be at t equal to T r, because if I differentiate this, I get that this is equal to 0. Okay. So, that is going to be, so this is the maximum. So, in other words, u max is equal to P naught upon k. What does that mean? That means that if the rise time is slow, okay, for all practical purposes, u max is the static response. Okay. So, we have this situation that you have that if T r by t is greater than 1, okay, then max will be in phase 2. Okay. So, now the question then becomes is this, that for T d by t larger than 1, because you see I showed this one, right, that this one goes on this particular value, it goes on for a long time. I mean, so T d by t greater than 1, okay. What we get is the peak factor is determined by the rise time. So, if T r by t is very fast, in other words, the rise time is very fast, means T r by t tends to 0, you get 2 P naught upon k. If rise time is very slow, T r by t becomes very large, then d is equal to 1. So, in other words, one of the things that comes out of this characteristics for pulse load is that if T r by t is much large, I mean, if if the duration of the load is such that the peak is during the first phase, which is the loading phase, then the peak value, dynamic amplification factor peak value, is actually dependent on how fast it rises. It can vary between 1 to 2 depending on how fast it rises and how slow it rises. See, if you look at this will give you an idea. If you look at this particular the shock spectrum that I showed you. If you look at the shock spectrum, right, rectangular really goes up fast. Okay? So, that is why in this particular, if you have very large duration, I mean T d by t greater than 1, if you look at this, this has the highest value. Okay? Half sine goes up, you see the sine goes up faster than the triangle. Okay? So, that is why this is larger. Triangle goes up the slowest, so it is the lowest. Okay? If I get the triangle to go really, really slowly, see it goes to 1. Okay? So, in other words, the triangle, if T d by t is large, the triangle really goes up slowly, it tends to 1. So, all of these points that I have made come out directly from this shock spectrum. Okay? And that is the reason why I showed the specific problem that I looked at, the rise time. Okay? So, that is a very interesting point of the pulse characteristics. Another characteristic to note is that if you look at when T d by t in a pulse load is very much less than 1. In other words, let us look at the rectangular. This T d for all practical purposes is it can't even see it. Okay? So, then let us look back at our response of the rectangular thing, and let us just look back at the rectangular response. What did we get? That note that if T d by t is very much less than 1, where will the max will always be in phase 2, because it can never get a chance to rise. Okay? And so, therefore, what we have is that u max is equal to P naught upon k. So, 2 P naught k sine pi T 1 t, where this is T d. Okay. Now, when T d by t is very, very small, what does this become? This becomes 2 pi P naught T d upon t upon k. This is nothing but omega. So, I will call that as P naught T d upon omega k. So, u max is equal to P naught T d upon omega k. Okay. And I am sorry, the omega is on top, omega T d upon k. Okay. Now, k is equal to m omega squared. Okay, I am going to substitute that in here, and so this is going to be equal to m omega squared comes here. So, this becomes 1 upon m omega P naught T d. So, u max is really, note that m and omega are characteristics of the structure. So, what is the loading? If you look at it, it is P naught T d. What is P naught T d? P naught T d, if you look at it, is really the area under the curve, which is known as impulse I. Okay? So, u max is equal to P naught T d upon m omega. Okay? So, now let us look at this, and that is that let us see if we can get that equation from somewhere else. Well, let us see. Let us consider that the structure is subjected to an impulse I. Okay. an impulse I. Then if you really look at it, this, if you look at the impulse momentum relationship, what does it say? It says m into the velocity. So, this is, what is this? This is the m into u dot is the momentum. The momentum is equal to 0 to T d, the net force, right. So, the net force is P t minus k u t d t, right. So, now, if you really look at it, if you have a very short duration load, okay, u t practically is 0. So, this basically becomes m u dot is equal to 0 to T d P t d t. And what is this? This is nothing but the impulse. So, essentially what we are saying is change of momentum is equal to impulse. So, if you take before this impulse was there, it was at rest. Okay? It was at rest. So, at rest meaning u 0 is equal to u dot 0 is 0. After the impulse has happened, which is over a duration T d, what is it? U of T d is still 0, because it is too short a duration, right. It is too short a duration for velocity to come into picture. However, u dot T d is equal to I upon m. Okay. So, now since u T d is practically for all practical purposes almost not there, I mean it is almost 0. So, then what does it become? My u max becomes equal to u T d cosine omega t plus u dot T d upon omega sine omega t, right. So, if you look at, so that is u t. So, u max is going to be equal to u T d squared plus u dot upon omega squared. Yeah. So, here u T d is 0, this is 1 upon, so square root. So, what do I get? I upon m omega, u max. The u max is I upon m omega. Let us look at this. What do I get? I upon m omega. So, therefore, the question then becomes the following, and that is that if your response, if your the load is extremely short duration, okay, extremely short duration load, okay, where T d by T is very much less than 1, okay, then u max is equal to integral 0 to T d P t, the area under the curve, upon m omega. That is what u max depends on. That is what u max is. So, therefore, note that it becomes very, very simple. Find out the area under the curve, divide by m omega, and that is your maximum value of this thing. And it is seen that in reality, as long as for the pulse load T d upon T is less than 1 by 4, this gives very low errors. So, this approximation is valid as long as T d upon T is less than 1 upon 4. Okay. So, this becomes a very, very interesting part of the entire characteristics. So, the pulse load characteristics give us two parts. What is that? If T d by T is much greater than 1, or at least greater than 1, then the dynamic amplification factor is essentially a function of the rise time. For example, the rise time for a rectangular pulse is very large. So, it is 2. Okay. For half sine pulse wave, it is relatively less than the rectangular, but more than the triangular, and so therefore, you saw that as your rise time goes down, okay, your dynamic amplification factor keeps going down. Okay. And furthermore, that if the rise time relative to the time duration is very large, okay, then for all practical purposes, the dynamic amplification factor is 1. In fact, the response is static. Okay. So, therefore, dynamic amplification factor varies between 1 and 2, as long as the duration of the load, duration of the load relative to time period, okay, T d by T is greater than 1, this is valid. Okay. If T d by T is much less than 1/4, then the maximum is given actually by the impulse divided by m omega. Okay. So, this is something that we get from the pulse load characteristics. And now, and we also looked at how to characterize impulse loads directly from that. Now, what I am going to do for the small time that I have is introduce you to the basic concept for generalized loading. I shall spend a lot more time on this in the next couple of lectures talking about it, but since I have introduced the concept of impulse loading, I will just give an idea of how this procedure is created. Okay. A generalized load is one which, and let us say it stops, it has a duration, but T d by T is sufficiently larger than 1. Okay. So, then what happens? How do I get the response? So, this is my P of t. So, generalized loading essentially means that I have a loading that lasts for a particular duration, but the duration is sufficiently large. So, that why am I saying that? It is just that I am saying that look, I do not have to look in phase 2, because my peak will occur in phase 1 itself, and let me worry about the phase 1 itself, because that will give me the response completely. So, how do I solve this problem? The way I solve this problem is the following, and I am going to first write down this solution for an undamped system. Okay. For an undamped system, what was the impulse load? If you remember, u of t is equal to I upon m omega into sin omega t. Okay. That is the response. Okay. So, now let me look at a P of t as a series of pulse trains. Let me look at them as a series of pulse trains, and let me assume that u dot and u dot 0 are 0. Okay. So, then what happens? Then let me look at this, let me look at the response at time t. Okay. So, if I look at response time t, then what happens? Okay. I can say that look, this what happens here, the response over here is starting at 0, okay, due to all these loads up to this point load, and that's the response. Okay. So, I can look at this load as a series of impulse trains, where each impulse is over something like d tau. Okay, I am using a dummy variable because t now specifies a specific value. Okay. So, specific value, it is no longer a variable, t is a specific value. So, I am using tau as the variable from 0 to t. Okay. So, if I take it as d tau, then I can look at it this way. So, if I take each one, what is the response due to each one individually? In other words, note that this at this point, if I am looking at this, I am only looking at as if this existed and all these did not exist. Then if you look at it, all I have is at instant. In other words, if I look at this particular thing, then, and since note that the system is linear, I can assume that these trains over here are, each of them is a separate load, and I could find out the response to each load, and then I could superpose the loading. So, if I did that, let us look at each individual load, what would be u of t equal to? U of t would be equal to 1 upon m omega into p of tau, because I am finding at a particular time tau, okay, d tau. Okay, this is the impulse, p tau del tau is the response at that particular instant of time. Okay. And from there, if I start my thing, what am I doing? I am doing sine omega t minus tau, because I am starting at time tau. Okay, I am looking only at this response, forgetting everything else. So, what would it be? If I look at the response due to just this one, it would be p of tau into d tau. Okay. I am sorry. It would be, if I look at this, if I look at time tau, okay, and I am looking at due to this alone. So, this one would be p tau, because it is tau, okay, and then I have tau plus d tau. So, this one, for all practical purposes, I could take the central value and call it as p tau and call it as even. So, if it is even, it becomes, what is the impulse? The impulse becomes p tau d tau, okay, and the response is going to be sine omega t minus tau, because the response was, the impulse was only given at time tau. Okay. So, therefore, since time tau was when it was given, so therefore, this is a shifted shifted time, t minus tau is a shifted time. So, this is the response, and therefore, if I consider all the trains, all I need to do is integrate from 0 to t. Okay. So, in other words, see, note that for a general loading, my response is equal to this. Of course, this is assuming u 0 is equal to 0 and u dot 0 is equal to 0. It means this is valid only if you have at rest conditions. So, this is actually, if you really look at it, this is nothing but, this is called the Duhamel integral, and this is nothing but a larger convolution integral, where u of t is equal to 1 upon m omega, sorry, not 1 upon m omega, the convolution integral is p tau h t minus tau d tau, where h t is equal to 1 upon m omega, okay, into sine omega t. this h of t is what? Let us look at this. Okay. Remember I upon m omega into sin omega t. So, this is known as the unit impulse response function. And look at this, this is purely a function of m omega, the m and the dynamic characteristics. It is just a function. So, it is basically a function which depends only on the structure characteristics, okay, structure dynamic characteristics, because m omega, and since this is undamped, xi is 0 anyway. So, the characteristics are only m and omega. This is the unit impulse response function. Okay. And the u of t is given as p t, p tau, where p t is the load, h t minus tau d tau 0 to t, and this is the classical convolution integral, and it is also called the Duhamel integral. Okay. And if we look at this, if I now extend this to a damped system, okay, let us look at this. I mean, we did see that you had a situation where u of T d is equal to 0, that impulse, T d is at the end of the impulse, and u dot T d is equal to I upon m omega. Now, this is the simple harmonic motion. So, if you have a damped system, for a damped system, what does it land up becoming? Okay. For a damped system, it lands up becoming simply, how do I get this? I get the response to be equal to, well, the following. This is m omega d, okay, because that omega d is what you get. So, I get u of t is equal to 1 upon m omega d 0 to tau p tau e to the power of minus xi omega t minus tau sin omega d t minus tau into d tau. Okay. This is nothing but the simple harmonic motion, and so this is p tau d tau, and so that is what you have, 1 upon this. That is the Duhamel integral for a damped system. Okay. So, that in a sense is a brief overview of how from the impulse response you can get to the this thing. Now, just for completeness sake, I will continue with this, but for completeness sake, I want to actually solve a problem that I want to go back to the harmonic problem, and I want to solve a problem which is known as the reason why I am introducing this over here is the following. This is also a harmonic. This is a simple harmonic motion. Only thing is that it is it is a complex. Okay. So, how do I solve this problem? This, and I am looking only at steady state. Okay. If we look at steady state, okay, the steady state will also have the form u 0 into e to the power of I omega bar t, the steady state response. Okay. So, if I substitute this, u dot is equal to I omega u e, and u double dot is equal to minus omega bar squared u into. So, if I look at it, what do I get? I get the following: k minus I omega bar c minus m omega bar squared into u 0 e to the power of omega I t is equal to p 0 e to the power of omega bar t. Okay. So, what do I get? I get it equal to u 0 is equal to p 0 upon k minus I omega bar c minus m omega bar squared. Okay. And if you look at this, this is equal to p naught upon k into 1 minus beta squared plus 2 I xi beta. That is my amplitude. Very interesting, and I shall continue with this concept a little bit further, because just like I showed that the generalized loading can be a solution, we can use the solution as the Duhamel integral. I now want to bring in another different concept, which is known as the fast Fourier transform. So, this is just an introduction to that, and therefore, I shall continue with this in the next lecture. So, now I just wanted to review what have we done till now. We have looked at the free vibration response of a single degree of freedom system. First, we of course developed the equations of motion. We have done the free vibration equations, free vibration response of a single degree of freedom system. We have done harmonic response of a single degree of freedom system. We have done response to periodic load. We have done response to pulse loads, impulse loads and general loads. At least one approach, the Duhamel integral approach, I looked at in brief. In other words, we have pretty much looked across the board at all kinds of dynamic loads that a single degree of freedom system can possibly face, okay, in a more mathematical manner, but at least we have looked at the variety of things. Okay. When we come to multi-degree of freedom system, of course, I still have a lot to look at from a single degree of freedom point of view, but when we come to multi-degree of freedom problem, we will not solve any equation, no mathematics. We will only see how we can use the characteristics that we have studied for each response for a single degree of freedom system and look at it. Okay? Thank you very much. Bye.